No control.
This we can. Oh, 13. No. Yeah. So more. Okay. Yeah, you can.
So the next talk will be by Raghuvansh on the topic noisy radio network load bounds via noiseless beeping lower bounds.
Thank you. I chose this paper because this particular question it's inspired by the East Canteen. And when you're having food in the East Canteen, you have the following situation. You have a number of people, and if only one of them is talking and he's saying X, then everybody gets to hear X. But there are a lot of people in the East Canteen, so very often it is the case that two people are talking, and then nobody hears anything, which is the same as everybody getting the dummy symbol bomb. So this could be called the East Canteen model of computation, but in the paper we chose to call it CAS. Yeah.
See, East Canteen with the people is listening.
Oh, is it? So the thing is that our term is very general. It also applies to this. But the CAS here stands for collision and silence, which means that if one person is talking, then the message goes through. If more than one person is talking, which is a collision, then you get this dummy symbol bot. And you get the same symbol if there is silence or zero people are talking. So the collision and silence model is one person is talking, you get the message. Anything else, you get this dummy symbol bot. And it is a model for wireless communication because the messages sent do not have an intended receiver. It's not that there is a wire connecting a sender to a receiver and the message goes from sender to a receiver. It's a wireless medium. You just transfer it into the medium and everybody hears the message. Okay. I would like to, so you can do computation in this model. Let's say every one of these parties has an input. Let's say it's a bit, which will be enough for the entire talk. So everybody has either a 0 or a 1. And let's say you want to count the number of people who have the 1. You want to compute the Hamming weight. You can do this by running a protocol. Everybody can just send their bit. You can count how many bits are 1, and that gives you the Hamming weight. So by defining protocols in this model, you can do computation. And I would like to study what is the effect of noise on this computation. Consider this exact same model, but you have stochastic noise on it. Yeah.
The channel is broadcast.
Yes.
And it is an go ahead, I have a question and planning was now. Properly.
Okay.
Properly expect you.
Okay, no problem. So we want to study the noisy CAS model. It is the same as the CAS, except in every round you have, yeah.
Do they share a clock or do
they share a clock? Everybody knows it's round IR.
Okay.
And everybody can decide to speak or
not. Okay.
Okay, so now in every round you have random noise, which means that whatever is the correct output, which is whatever you should have gotten in the model I just described, you get that with probability 90%, and with 10% you get something else. And this constant is the probability of it. So in noisy CAS, if one person is speaking, it is 90% likely that you get the correct bit. But with the remaining 10%, you can either get a different bit or you can get the bot symbol or anything like that. And same for if there's a collision or if there is silence.
So here when you mean the get, is this a function of the receivers or is it a function of the sender? Like in the sense that when is it possible that the sender says something, but some of them get the symbol, but some of them get bot?
That's a good question. So the noise we have is correlated, which means everybody always gets the same thing.
Okay.
The noise actually happens at the sender. Suppose you're trying to send something, it can be corrupted with some probability, and then everybody will get that corrupted. But they all get the same thing.
And if there's a collision, there is no chance of getting anything out of the bot.
You could. Let's say there's a collision, but somebody was speaking louder than the other, so you get his bit. There is some probability that you get something. This noisy CAS model is weaker than the CAS model because noise can only hurt your system. You are no longer sure about what the bit was sent. And the question we want to study is exactly how much weaker it is. What is the slowdown of running the same protocol or computing the same function in the noisy and the noiseless model? For example, I just told you a protocol for the Hamming weight, which is everybody sends the same bit. This is a noiseless protocol because you reliably get the correct bit. Suppose I wanted to compute the Hamming weight in the setting with noise. What is the length I need? What is the number of rounds I need to do this? And because the noisy model is only weaker than the noiseless model, the best you can hope for is you can have a constant overhead or one overhead, which is that the length does not change whether it's noisy or noiseless. And in fact, the worst you can hope for is your overhead is log n. This is because the noise is random. And one thing you can always do is you can repeat the protocol, repeat the round log n times and take the majority. Because each particular repetition is correct with probability 90%, the majority will be correct with except with probability at most a small polynomial. Let's say n is the number of rounds. Can union bound over all of these rounds, and you get to the whole protocol is reliable, except with probability a small polynomial. The overhead of log n, it's the worst possible. The overhead of constant is the best possible. And what we are trying to find out is what is the right answer in these two limits.
So there are whatever n people who are communicating.
So I'm being a bit. I'm using notation a little bit. I'm using n for people and also for the rounds. Because it's a log, it doesn't matter. The rounds will be polynomial in n, but I will be using n for both.
They all have identifier. There's some way to break it.
Yes, you know who's the first person, who's the second person, who's the third person.
Protocols will say
Yeah.
who goes first.
Yeah. And I'll be only dealing with polynomial and protocol, so the log n it will be the same whether it's people or rounds. Okay. In a paper a few years ago, this was actually the first paper I wrote. It was not the first paper that got published, but it was the first paper I wrote. And in this paper, we consider the same model, and we show that if your original noiseless protocol is non-adaptive, this is a restricted set of protocols. I will tell you later what it is, but if you are in this restricted set of protocols, then you can be resilient to noise. You will no longer be non-adaptive. The protocol you get will be adaptive, but it will only be a constant factor longer. Okay? So non-adaptive means that even before the protocol starts, you know who is speaking in what rounds. You know that player 1 is speaking in round 1, and let's say player 5 is speaking in round 2, and so on. If you have this information that does not change during the execution, then you are non-adaptive. And if you have such a protocol, then we show that you can make it noise resilient with only a constant overhead, which is the best possible we can hope for.
So non-adaptive does mean that who speaks is non-adaptive, or what they speak will depend on previous.
What they speak can depend on everything, but who speaks will be non-adaptive. And this also means that if there's a collision, then that is actually not helpful, because if you know that there's going to be collision, you also know what is going to come out of it, which is the box input. So this is a rather restricted model because it takes away the power of collisions, and you have to make sure that it's only meaningful if only one person is speaking every round. But if you have such a system, then you can make it adaptive with only a constant overhead. And the question we deal with in this paper, it's the more general question. Suppose you have general adaptive protocols in the noiseless setting. We show that if you want to make protocols like this resilient, then you have to pay the worst possible log n overhead. Okay, so if you are in the restricted case, then this is actually very easy, but adaptive protocols are much more powerful, and to make them resilient requires a much higher overhead.
So not all adaptive protocols, right? You show that they exist in the adaptive protocol.
Yeah, of course. It can't be about all adaptive protocols because non-adaptive protocols are a subcase. Yeah.
So it's the concept that if we know that a bit could exist and they want to make sure that everybody is.
I can't hear you. What is it?
So I confused about the model. So is the following true that every node has a bit and they want to make sure that everybody is eventually? Is that?
No, that is one function. In general, everybody has an input xi, and they want to compute f of x1 to xn. There is some function f that they want to compute.
By talking to.
Yeah.
There's a dot touch from each party to everybody else.
Yeah.
Any dot touch.
Yes. Correct.
By theta 1, you mean that the stochastic noise is one minus, it's correct with probability 1 minus epsilon and erroneous with probability epsilon, and the blow up is only a function of epsilon. Is that what you mean by theta 1 here? Or
Yeah.
are you fixing this epsilon to be like 10% and then working with it for the electrons.
I'm fixing epsilon to be 10%, but if it is smaller, then it means the probability of error is smaller, right? So it will only help us. That comes in if epsilon is larger, then you have to talk about error with probability half minus epsilon, then that comes in. But here you can fix it or something. Okay, so like I said, this is the main result. We show that the gap between the cast channel and the noisy cast channel is at least logn. This is also tight because it's been repeated logn times. And the main lemma underlying this result is that the gap between the cast channel and a beeping channel, which is what I'm going to define, it is also at least logn. And this will also be tight. The reason why the lemma implies a theorem is because there's a nice argument that I will not go into, but it shows that if you have the beeping channel is stronger than the noisy cast. So if you have a lower bound for beeping, then you'll get a lower bound for noisy cast. Yep.
I have a question about the model. So I'm just trying to understand how is the collision affecting you, because you're saying they all run on a common flaw and any program and they all have some identifier. So protocols can say at time step 0 this person does this, time step 1 this person does this, and so on. So if at every point only one person is saying something, then when is the collision?
So those are non-adaptive channels.
That is, so let me say it in more detail. So the protocol you described where you know when everybody is speaking, that is a non-adaptive protocol. In general, you can have adaptive protocols. And one nice example is suppose you want to compute the OR of all the things. If you want to do it non-adaptively, you'll need n rounds because maybe only one of them has it and that's the last person. But if you want to do it adaptively, you can say something like if you have a 1, you speak. And then you'll be able to, so there may be collisions, but we can remove the collisions in polyglot rounds and you'll be able to do it as a polyglot round. So adaptive protocols are actually much more powerful. So what was I? Yeah, so we will show that there is a logging gap between cast and beeping, and that will imply a logging gap between cast and noisy cast. But important here is that after this lemma, there is no noise anywhere. What I'm going to show is the separation between noiseless cast and noiseless beeping, and that will imply our noisy cast result. But after I state this lemma, there will not be any noise anywhere. Everybody will have the correct bit received in every round. Yeah.
So what about between non-adaptive cast and non-adaptive noisy cast?
So that actually it is for correlated noise, the overhead is logn, and the way to see it is suppose everybody has a bit and you want to know all the bits, then when you don't have noise, it's n rounds. But if you have noise and it's non-adaptive, then anybody who's taking less than logn rounds, it will be disruptive. Yeah. So that is what. Yeah. So another thing is that this cast channel is a specific instance of what we call F channels. Here, an F channel is just a channel whose output is a function of the number of people that are speaking. So in a cast channel, if one person is speaking, then you get the bit. Here, there is a slight discrepancy that you get the actual bit and not just the number, but we can get around it. We can have a separate round for 0 and 1. But basically, an F channel is something where if n parties are broadcasting, then you get F of n. And you can replace cast by any F channel, and this result will still hold. So what is this beeping model that is weaker than everything? And the beeping model is simply the OR channel. Suppose you have n parties. In every round, the parties can say a bit, which is 0 or 1. And what the parties receive is the OR of all the bits. If all of them are beeping a 0, then they will all get a 0. On the other hand, if there is a subset that is beeping a 1, then all of them will get a 1. And that's the beeping channel. So I have to show you that this beeping channel is logn weaker than the cast channel, which means I have to show you a function for which there is a protocol of, let's say, T rounds in the cast channel, such that any protocol on the beeping channel is at least T logn. So I have to show you 3 things. I have to show you a function, I have to show you a protocol, and then I have to show you a lower bound. Let's do them in order. The function is what I would call the group-wise counts. You have n people, divide them into groups of size root n. You have root n such groups. And I promise you that in each group, each player has an input that is 0 or 1. And in each group, either 1 or 2 players have the input 1, and everybody else has a 0. Okay, and you have to determine which is the case. So you have to output root n different values, one for each group, and that value should tell me it's a bit whether in that group there's one person with a one or there are two people with a one. Okay, this is the function. There is a protocol for this function of length root n, which is the number of groups in the CAS model, because you can go group by group, and you can simply ask everybody who has a one in that group to speak. You'll do this in the same round. Now, if one person has a group, then you will get a proper bit. If there are two people with a one, then you will get a bot. You can differentiate between them. Like I said, there is no noise anymore. So in root n rounds, one for each group, you will be able to output the root n length vector, and that's your whole protocol. Now I have to show you, go back. Now I have to show you that any protocol for over the beeping channel for this group-wise count function has length at least root n log n. And for that, let me introduce you to Fooling sets. And I'm not introducing Fooling sets to you because they will apply to the beeping channel, or this will show the lower boundary we want. But it's just something cool that you should know. I'm kidding, they will apply to the beeping channel eventually. So a Fooling set is, let us go back to two parties. Party one has input X and party two has input Y. Then a Fooling set is just a set of pairs of inputs. A pair is Xi, Yi, and the I greater than 0 are the elements in the set, such that all of these pairs have the same function value, they have the same output. So f of Xi, Yi is the same for all I. But every time you do a cross term, every time you take an I and an I prime which is different from I, and you take X from the pair I and Y from pair I prime, then the function value is different. Okay, so all the Xi's, Yi's, they evaluate to say 1 over the function, but Xi, Yi prime will evaluate to 0. And such a set is called a Fooling set. And the Fooling set technique is basically a lemma saying that if you have a Fooling set of size S, then that means protocols must have length at least log S. Why is this true? The reason this is true is two-party protocols, or at least two-party deterministic protocols, they correspond to rectangles in the following sense. Suppose you have two parties, Alice and Bob. Alice's inputs are the rows of this space, and Bob's inputs are the columns of this space. Suppose the first message goes from Alice to Bob, it is M1. This is a function of Alice's input. So let's say for the top portion of these inputs, the function is 0. And for the bottom portion, the function is 1. And in this sense, the message essentially divides this space of inputs into a top part and a bottom part, which corresponds to the message being 0 and the message being 1, respectively. Let us go to the next round. Here, Bob sends a message M2. It's a function of M1 and his own input. And again, I claim that this divides the input space vertically this time into a left half and the right half differently for each of the two parts. Why is that? Because if Alice's message is 0, then again, for some inputs, Bob will send some M2 equals 0. For other inputs, he will send M2 equals to 1. And the left part is just the inputs for each equals 0, and the right part is just the inputs for each equals 1. For M2 equals to 1, you will again have a partition. It will be different because it depends on the message M1, but you will still have some partition. You can keep going this way. If you have n messages in your protocol, that means that you have partitioned your input space into 2 to the n rectangles. And the claim is any such rectangle can only have one element of a Fooling set. Why? If you have two, let's say you have x1, y1, and x2, y2 in the same rectangle, then because these are rectangles, you must also have x2, y1 in them. This will not be true for an arbitrary shape, but because this is a rectangle and you have x1, y1, x2, y2, you also have x2, y1. But we know from the Fooling set property that the function value for x1, y1, and x2, y2 is different from that on x2, y1. So these two cannot have the same transcript because then the protocol will be incorrect for at least one of them. Okay, so this is essentially the Fooling set technique. If you have a Fooling set of size S, then each of those elements must be in a different rectangle, which means you must have at least S rectangles, which means the protocol must be of length log S. Okay. A textbook example of this technique is the equality function. Suppose the inputs are n bits. It is equal if and only if you're on this diagonal, if x is equal to xp. And I claim that all of these cells, they form a Fooling set. Because every time you take a cross term, which is here or here, the redder ones, then you're in a not equal situation, but on the correct diagonal, you're in an equal situation. So all of this is a pooling set. You have a pooling set of size 2 to the n, which means your protocol, your deterministic protocol must have length n for equality. Okay. The catch about the pooling set technique is that it only shows lower bounds for deterministic protocols. And moreover, this technique does not work for the beeping model. And these will be the two problems we have to overcome. I have this technique that I want to use, but it only shows deterministic lower bound. See, I want to show randomized lower bound. And it does not work for beeping, but I want to show lower bound for beeping. So how do I overcome that? Firstly, let me tell you what is the problem in applying this technique to the beeping model. And the problem is that the transcripts of the beeping model, they do not correspond to rectangles. We just thought how if Alice is sending messages to Bob, then that partitions the input space nicely into rectangles. But here, if both of them are sending a bit and they're getting the transcript as the OR of the bits, then you no longer have this property, because let's say Alice is sending a 0, Bob is also sending a 0, then the intersection is this rectangle 0. But if you are told that the OR is 1, then it can be in one of these three situations. Either one of them, either Alice sent a 0 and Bob sent a 1, or both of them sent a 1, or Alice sent a 1 and Bob sent a 1. And the union of these three things is no longer a rectangle, so you cannot apply the pooling set technique. Okay? So we have these problems. We cannot apply the pooling set techniques for beeping because the transcripts are not rectangles. We have another problem that it shows deterministic lower bounds and not randomized lower bounds, but we want to show randomized lower bound. Nevertheless, let me show you that the function that we talked about, it has a very large pooling set. So it doesn't give you anything, but it's nice to have a pooling set. And the pooling set that I want to talk about is these tuples, they are groups, and the coordinates in each tuple, they are the players. They are the inputs of the players in a group. So you have root n groups and root n players in each group. And I want to consider inputs of the form where every group has exactly one player with an input 1. Okay, so some such input may look like this, where the first player in group 1 has a 1, the last player in group 2 has a 1, and the third player in the last group, it has a 1. And I claim that the set of all of these inputs, it forms a pooling set. Why? Take any two such inputs. Because they are different inputs, there exists a group where the player that has a 1 is different. Now, the way you construct your cross term is you keep everything from the first input, but for the player that is different, you take it from the second input. And now this cross term, it is different for the function because in the original case, you have to output that for every group has only one player. But for the cross term, you have to output that every group has 1, but the first group has 2. Okay? So all of the elements in my pooling set have the same output, which is every group has 1. But any cross term that I construct this way, it has another correct output, which is that every group except 1 has 1 and that group has 2.
What's the difference? How do you construct the language? I mean, like what's the
The hybrid is that every party's input should come from one of the two inputs.
it's or it's just important. So that
So when I'm talking about a hybrid, let me go back. If you're constructing hybrid, then the x comes from one pair and the y comes from another pair. That's all I want. So even here, this 0, where is it? This 1 comes from this 1 comes from this, and everything else comes from the top.
So
That's all.
okay. So this is one of the cross terms we could have obtained.
Yeah. You could have told many more.
Okay.
But this is one of the cross terms, and in fact, any cross term is fine. Any cross term, it will. If you're interested for, if you are inside the rectangle, then all the cross terms are inside the rectangle.
Yeah.
So it is fine to be incorrect on some cross term. Okay, so this is one cross term that I'm incorrect on, which is a problem. Okay, what is the size of this pooling set? I have root n groups, and each one of them has one player with the input 1. So there are root n choices for root n groups, which means there are root n to the root n elements in the pooling set. The lower bound that this will give us is the log of the size, which is root and login, which is exactly what we want. But like I said, we have two problems that we have deterministic lower bounds that do not work for beeping. So let me tell you how to get around these problems. First, I'll tell you how to get randomized lower bounds from this technique. And essentially, the way you get this is you do this in the distribution setting. Every possible input will have a probability. And you show that the probability mass of all the incorrect hybrids, of all the hybrids, is larger than the probability mass. It's not larger, it's on the same scale as the probability mass of the correct hybrids. There is a distribution that I will not go into that we work with, but essentially what we want to show is that instead of showing one cross term, you can show many, many different cross terms. And that will, the number of cross terms will increase the probability mass, and that will imply a randomized lower bound. Why are there many, many cross terms? The reason is if you are in a rectangle, either the rectangle is small, in which case there should be many rectangles and you already have a lower bound. Or if the rectangle is large, then it has many possible red inputs that you can take hybrids from. In particular, you can have a 1 here, you can have a 1 here, you can have a 1 here, you can have a 1 anywhere here. And same for all the groups. So you can have almost n possible inputs that you can take a hybrid from. So every black input will generate n possible bad hybrids. And this number is large enough that for the right distribution, it will mean that you have a distribution lower bound. Okay, this is probably unclear because I haven't told you what the distribution is. But the idea is because you're generating a lot of hybrids, that will make sure that the probability mass is large. Okay. The second problem we had was that pooling sets do not work for beeping. So what am I even talking about? And the way we fix this is by observing that the hybrids we create, they only change the input of one party. Okay, so we had these two inputs. We are able to create a hybrid, but this hybrid was only changing this second party in the first group. And why is this helping us? We have n different parties, and we only want to show a lower bound of root n times log n. So most of the parties that are there in the system, they're not even talking. And we can freely change their input, it will not affect the actual transfer. It will only affect it if the party that is being changed is crucial to one of the rounds. If it's that's the only party that is beeping in that round, otherwise it will not change the transfer at all. There are a small number of such parties. It is bounded by the length of the protocol, which means most of these hybrids you can change while being in the same transfer. It will not take you outside the rectangle, and therefore this gives you the lower bound. So only one pair is affected who doesn't even speak, and that was the last slide. That's how you get the lower bound.
Especially here to use the fact that there's root, you're shooting for root n.
No. Anything.
No, but the fact that it won't affect most of the parties. Isn't that because you are going for a root n lower bound?
I could have gone for n to the 0.9 lower bound if I took n to the 0.9 groups and groups the size n to the 0.1. That would still be fine. I just want the number of parties that you removed here, which is the length of the protocol, to be smaller than n, which is still fine. More questions? Yes.
Can you maybe say a little bit about how do you incorporate noise in that process? Like once you have this lower bound,
Yeah.
where did the
Okay, so let me go back. I have to show you that a beeping lower bound implies a noisy cast lower bound.
Yes.
Equivalently, I can show you a noisy cast protocol, a protocol resident to noise in the cast model implies a protocol in the beeping model. Here's how you do it. You take every round of the protocol here. You take every round and you replace that round by 2 rounds. In the first round, everybody who's speaking, a random subset of the people who are speaking, they will speak in the first round, and the complement will speak in the second round. Now, if nobody is speaking, then nobody will be speaking. You'll be able to get it. If one person is speaking, then only one of them will be speaking. Again, you will be able to get it. If more than one are speaking, then except with some error, you will have 2 things. So you can repeat it many times, but you can make it as small as you want. But with some error, except with some error, you'll be able to also detect that. So you can essentially emulate this for the beacon channel. Good. More questions? Good. That's it. Thank you.
Okay, just a couple of quick announcements. So tomorrow we start at 9:30 and at 12:30